Okay, why did a tech giant like Java actually need to be invented? Let's dive right into this explainer. We're going to go way under the hood today to explore the origins and architecture of Java, unpacking the fundamental why behind modern software engineering.
We've got a pretty clear roadmap for this one. We'll start by looking at the pre-Java world, tackle the portability problem, and then break down Java's brilliant solution, the JVM. From there, we'll hit the write once, run anywhere paradigm and wrap up with simplicity and security.
Section 1, the pre-Java world, featuring assembly, C, and C++.
Right, so to really understand why Java was such a game changer, we have to look back at the 80s and 90s. Languages like C and C++ absolutely ruled the world. Why? Well, because they sat incredibly close to the hardware. They were blazingly fast, but inherently rigid. And to grasp that rigidity, we need to clearly define what a platform actually is. It's not just a generic computer, it's the highly specific pairing of a hardware processor, like an Intel x86 or an ARM chip, and a software operating system, like Windows or Mac.
And because of that specific combo, code behaves entirely differently from machine to machine. I mean, if you just want to print some text to a screen, Windows uses a completely different OS library than Mac does. And down at the silicon level, an Intel processor literally speaks a different physical grammar of ones and zeros compared to an ARM processor.
Section 2, the portability problem. Because these platforms spoke entirely different languages, C and C++ were completely platform dependent.
So you might be asking yourself, why couldn't I just run my compiled code everywhere? What's the big deal? Well, the answer lies in how traditional compilers worked. A compiler translates your human-readable code into the machine code that a computer actually understands, right? But those traditional compilers, they were strict locals. It was a total deployment nightmare for developers. Say you compile your code for an Intel Windows machine. Boom, you get machine code A. But if you take that exact same code and try to run it on an ARM Mac, it fatally crashes. No way around it. You're basically forced to do this incredibly tedious manual process of tweaking and recompiling your code from scratch for every single hardware setup out there.
Section 3, Java's translator, the JVM. Let's look at how the creators of Java totally flipped the script to bypass this massive bottleneck.
Instead of compiling straight down to machine code, Java introduced this ingenious two-step flow. You write your Java file. The compiler translates it. But, and here's the kicker, not into zeros and ones. It translates it into an intermediate state called bytecode. Then a brand new piece of software called the JVM steps in to take that bytecode the rest of the way.
Think of it like traveling. If you're going to China, C++ essentially forces you to fluently learn the local dialect before you can do anything. Java, on the other hand, says, hey, just speak your one universal language and bring a local translator friend along to do all the heavy lifting for you.
So your bytecode is strictly universal, but the translator, that Java Virtual Machine or JVM, is platform-specific. You only ever write the bytecode once. All that messy work of talking to Windows libraries, macOS, or an Intel processor, that is entirely abstracted away. The local JVM just handles it.
Section 4, write once, run anywhere. Because the JVM takes care of that local translation, developers were finally unchained from their hardware constraints.
Write once, run anywhere, or WARA. This literally became the ultimate anthem for Java developers. It shifted the paradigm of software engineering forever. You compile into your universal bytecode exactly one time, and it runs on absolutely any machine on the planet, as long as it has a JVM installed.
And honestly, this portability hit the market at the perfect historical moment. We were shifting away from just basic desktop PCs to this sudden, massive explosion of smart TVs, set-top boxes, and back-end internet servers. Imagine recompiling C++ from scratch for every single new server architecture. It would have completely crippled the internet boom. Java's universal paradigm swooped in and saved the industry from a massive bottleneck.
Section 5, simplicity and security. Portability was a huge win, obviously. But to truly dethrone the C++ era, Java had to fix two other major flaws: complexity and a severe lack of web-facing security. So the creators of Java explicitly threw some of C++'s most frustrating features straight in the trash. They completely removed complex pointers, cleaned up the messy logic of multiple inheritance, and, perhaps most importantly, they introduced automated memory management. That meant developers no longer had to manually deallocate memory, which literally wiped out thousands of fatal bugs overnight. A real game changer.
Now, regarding security, in the early days, Java wasn't just for back-end servers.
Java applets were actually being beamed across the internet directly into users' front-end web browsers. But think about it. If you're downloading random bytecode from a total stranger on the brand new interconnected web, how do you know it won't just completely erase your hard drive?
Well, to solve this, the JVM utilizes what's called a sandbox model. It basically acts as a strict security guard, forcing that bytecode to play inside a highly restricted space. It completely denies unknown code from accessing your private files or messing with your operating system resources. It protects your hardware.
Which leaves us with a pretty fascinating question to wrap up on. If this model was so revolutionary, why didn't C++ just copy it? Well, languages like Python and C# absolutely did adopt this exact platform-independent model later on. But C++? C++ flat out refused. Adding a JVM inherently adds a tiny fraction of processing time, and C++ chose raw, unadulterated hardware speed over absolutely everything else. Java, on the other hand, shows universal portability and security. So the next time you write a line of code, ask yourself, are you optimizing for the machine or are you optimizing for the world? Thanks for joining this explainer. See you next time.